Hello everyone, my name is Patricia Arroyo and I come from the University of Extremadura, and today I'm going to talk about how we can turn raw sensor signals from electronic noise to reliable odor information. The electronic noises are powerful tools for environmental and industrial applications, but the real intelligence comes from the data processing pipeline, not just the hardware. My goal here today is to show how we move from electrical responses to actionable insight. I will follow this outline during the presentation. First, we have an introduction, and then the pipeline overview to frame the journey from signal to the decision, the odor decision. And we will finish speaking briefly about the sensor fusion and challenges and trends. Okay, so odor monitoring matters because it touches public health, food quality, and environmental compliance. But unlike laboratory analyzers, an electronic nose doesn't measure a single compound. It records a multi-sensor pattern. Each sensor is cross-sensitive, so we must interpret complex and overlapping signals. Also, we have, of course, the environmental factors, okay, especially temperature, humidity, and the sensor drift that constantly distort those sensor signals. Then, if we don't compensate them, our models fail in the field. So the challenge here is clear. We have to turn this noisy and unstable data into something trustworthy. To do that, we use this processing pipeline that transforms these raw sensor signals into useful odor information. And we start here on the left with the signal acquisition. This is where the sensor array produces the raw measurements. Then we move to the first real stage, the signal preprocessing. This block cleans the data, producing normalized measurements. And next comes the future extraction. Here, we capture the essential behavior of each sensor, creating what we call a future vector. And then we have the following step, which is the dimensionality reduction. We have to reduce the complexity of that feature vector into a low-dimensional representation. That is going to be easier to visualize and also, of course, to process. And after that, we reach the learning. The machine learning algorithms classify or quantify the odors based on these features. Then we will have a trained model or its prediction. Okay, and finally we have the deployment, where these models runs in real time, and we will deliver some actionable odor information to the end users. For example, some kind of alerts or something. At the top, you can see end-to-end deep learning, which connects the raw measurements directly to prediction. And at the bottom, there is a feedback loop. This is for recalibration and drift monitoring. So let's start with the first stage. Drift is the silent enemy of long-term monitoring. And for that, we use a baseline tracking algorithm that continuously adjusts the reference point. In that way, a measurement today can remain comparable to one taken, for example, 2 months later. Then for noise reduction, we have low-pass filters that remove high-frequency components or medium filters that eliminate these kinds of impulsive spikes. Finally, we have environmental compensation models that correct the temperature and the humidity effects in real time. And with these three steps combined, our data becomes robust and repeatable. So next, we can focus on what information the signal actual contains. So now that our signals are clean, we move to the next block in the pipeline, the feature extraction. The feature extraction transforms this time series data into some quantitative descriptor. And we use both steady state features, like for example, the maximum response or the area under the curve, and or dynamic features, for example, the rise time, the decay time, or the response slope. Moreover, there are advanced approaches that include frequency domain analysis to capture this kind of spectral characteristics, or wavelet analysis to reveal transient signal features. And finally, we also have a manifold learning that combines extraction and dimensionality reduction in a single step. So we have extract that feature, and now we have a high dimensional feature vector, which is a kind of fingerprint of the odor. However, high dimensionality creates its own problems. We have redundancy and overfitting. And that's why the next step is to reduce and simplify this space. For that, we apply methods that compress the information while preserving the essential structure of the data. The classic approach is the PCA, which is a linear method that reveals the main variance direction, and it, as we know, is an excellent tool for visualizing the cluster separation. But when we have non-linear relationship, we use another kind of methods. For example, we have the TSNE, which focuses on local neighborhoods, and it is ideal for showing small odor clusters, while, for example, other techniques like UMAP balances local and global structures and scales better when we have a large data set. Okay, but here the goal it is not just the compression, but also understanding the intrinsic manifold where real odor patterns reside. And once we have this representation, we can train our machine learning models, the heart of the pattern recognition. For applications that involve unknown or involving other sources, unsupervised and semi-supervised learning methods are critical. For example, unsupervised clustering methods reveal hidden structures in unlabeled data and allows us to detect anomalies. For example, DB scan, one of these techniques, is particularly useful for irregular clusters. On the other hand, we have also semi-supervised techniques. These techniques use a small labeled set to guide the learning on a large unlabeled pool. Okay, so these methods enable models to adapt to unknown other sources without requiring extensive manual labeling and reducing operational costs. But if we have labeled data, we can use supervised algorithms. We have a spectrum of choices. On one end, we have the classical methods. These are highly interpretable, efficient, and often perform very well on smaller and well-defined datasets. On the other hand, when we need quantitative prediction of an odor concentration, we need to use regression methods. And finally, on the other end, we have neural networks. These techniques offer the potential of higher accuracy, especially when we have a complex and non-linear data, but they demand to have larger data sets and come with an increase, of course, in computational complexity. Within this, there are some algorithms that allows us to skip many of the steps seen so far in the pipeline. And we achieve this with end-to-end deep learning algorithms, the most advanced approach, but also the most demanding. Deep learning models can learn features automatically from the raw signals from the sensors. This eliminates the need for manual feature engineering, which we just discussed, saving, of course, a lot of development time. For example, we have convolutional neural networks, which are particularly effective for spatial temporal responses mapping. Like it is good with like photos of the odor. And on the other hand, we have the recurrent neural networks and the long short-term memory architectures, LSTM, which model temporal dependencies in dynamic odor exposures. It works very well with temporal series. And this is crucial for real-time monitoring. And now let's see how we maintain accuracy over time and across different devices. The calibration. Okay, the standard calibration needs reference, measurements, and the control condition, a process that is both costly and time-consuming. In the field, calibration becomes even harder because odor composition and environmental conditions change constantly. That is why it is interesting, the adaptive calibration, which continuously adjusts the system parameters to compensate the drift in the sensor in real time. So this adaptive calibration keeps the signal stable without the need for frequent manual recalibration. Now, the transfer learning allows a model trained in one environment or on one device to be reused in another one with, of course, minimal retraining. The final piece of the puzzle is the deployment, which is important on edge computing and the Internet of Things. For real-time operation, we bring the intelligence to the edge. That means we process directly on the sensor node, okay? Low-power microcontrollers or single-board computers run these models, but we will have compressed models to generate, for example, instant odors alerts to the end user. Then, while the edge handles this kind of inference, the cloud, on the other hand, adds results for mapping and trend analysis. In this way, each device improves the global model without sharing raw data and keeping privacy and we will keep also the bandwidth of the communication and the control. Finally, an increasingly important component of odor monitoring is the sensor fusion, which means that we combine signals from different sensor types. For example, metal oxide sensor, humidity, temperature sensor, optical detectors, on other kind of technologies, sensor detectors, gas sensor detectors, and we can merge them at 3 levels, depending on if you are concatenating raw data, features, or the final decision from the classification stage. By combining complementary sensor types, the systems are going to achieve improved robustness and accuracy that is going to be enhanced. And of course, we can correct the environmental interference. Finally, despite this progress, significant challenges remain. Okay, we have, for example, the long-term drift compensation, which is difficult to predict and to correct. We have the model generalization across diverse environments, which remains problematic. And we also have the complex odor mixtures, which are very challenging to detect and quantify accurately. On the other hand, the future direction in this field points towards adaptive and self-calibrating models that automatically are going to adapt to sensor drift and these kind of environmental changes. We have the resource-efficient edge computing with lightweight architecture that are going to enable deployment on ultra-low power devices. And finally, a standardized benchmark will enable meaningful cross-study comparisons. And that's all. Thank you for your attention. Sorry for my English, and I hope this talk has been useful for you.
Thank you very much, Patricia. Now the session is open for discussion. If you have any question, please use YouTube channel and input the question in the chat window.
Yeah, I'm going to
Okay, there is one question.
For example, Peter, can these learning models run on low power embedded devices? Oh, okay, that's a very relevant question. In general, deep learning models, especially this one, the convolutional neural networks and recursive neural networks, are quite computationally demanding. So if we want to run the full version of these networks in real time, it's going to be very difficult, okay? Because on a low power microcontroller, it is usually not possible. But we can deploy simplified or compressed version of these architectures. We can use some kind of techniques to reduce the size and the energy the consumption of the model. And we have another strategy. For example, we can use a hybrid strategy where we can run locally this kind of models in some kind of gateway or edge node with higher capacity, and keep the edge node just with another kind of more reduced or consuming models.
Okay, now the time is up. So thank you very much, Patricia.
Thank
I'd
you.
like to move on to the next presentation. Thank you very much.